In this video, we're going to apply integration by parts to solve some definite integrals. So here we have evaluate from 1 to e log x dx. Let's rewrite the integrand so we have a product of two functions. So what we have is integral from 1 to e log x dx. That's equal to integral from 1 to e log x times 1 dx. And then we're going to apply the integration by parts. So we're going to let this part be u is equal to log x, and this part will be dv. Alright, so what we have is the integral from 1 to e log x dx. We'll let u be equal to log x. Its derivative du is equal to 1 over x dx. We'll let dv be equal to 1 dx, and the antiderivative of 1 is just going to be x. So we're basically integrating both sides. Integral of dv is just going to give us v, and integral of 1 will give us x. Let's put this in a box. Alright, so what we have is integral from 1 to e log x times 1 dx. This is equal to u times v. U is log x, v is x, minus integral of v, which is x, and du is 1 over x dx. Let's label these. So we have u is log x, 1 dx, that's dv. That's going to be equal to u times v, so this is u, and this is v is x, minus integral of v, which is x, times this part, 1 over x dx, and that's du. And let's not forget the limits. So evaluate it from 1 to e, and evaluate it from 1 to e. Alright, so what we have is integral 1 to e log x dx will be equal to x log x from 1 to e minus integral, the x's cancel out, and we get integral from 1 to e 1 dx, and we get x log x from 1 to e, and integral of 1 and the derivative of 1 is just x, minus x from 1 to e. Now it's easier just to write this as x log x minus x evaluated from 1 to e, rather than writing it as two pieces evaluated from 1 to e. This avoids making small arithmetic errors. So applying the fundamental theorem of calculus, we put the upper limit in, plug x equals e in, and we get e log e minus e minus, now plugging the lower limit in, we get 1 log 1 minus 1. Log of e is 1, log of 1 is 0, we get e minus log 1 is 0, minus minus is plus, we get plus 1, e minus e is 0, the answer is 1. So what we have shown is that integral from 1 to e log x dx is equal to 1. Let me clean this up a little bit. Integral from 1 to e log x dx is 1. Alright. So now let's look at another example. But before doing that, let's go over a strategy. So we choose u to be the function that comes first on the list. This is a light principle. So we're going to let u be equal to log x because that's the first that comes on the list. L stands for logs, I stands for inverse trig functions, A for algebraic function like 1, x, x squared, T stands for trig functions like sin x or cos x, and E stands for exponential functions like 2 to the x, 3 to the x, or e to the x. So we're going to let u be equal to log x because that's the first that comes on the list. That's the first choice for u. So u is log x. Its derivative is going to be 1 over x dx. And we choose dv to be the remainder. dv will be 1 dx. And the antiderivative of 1 is x. So this is just going over the strategy of why we chose u to be equal to log x. Alright, let's look at another example. Here we have integral from pi over 6 to pi over 4 x times secant squared x dx. So what we have is integral x secant squared x dx. So according to the light principle, we're going to choose u to be the function that comes first on the list, and the algebraic function x comes first on the list. The trig comes later. So the algebraic function, that's going to be x, so we let u be equal to, u is equal to x, u is equal to x, and du is equal to dx. dv will be the leftover, that's secant squared x dx. And now integrate both sides, and integral of dv will give us v, and integral of secant squared x will give us tangent x, because derivative of tan x is secant squared x. So that's what we have. We have u is equal to, that's our choice for u. And once you choose u, then everything else is going to fall into place. So we choose u to be x. If this is a choice for u, then whatever is left over has to be dv. All right, so what we have is integral from pi over 6 to pi over 4, x times secant squared x dx, and we let u be equal to x. du is equal to dx. dv is secant squared x dx, and v is the antiderivative, that's tan x. Let's put this in a box. All right, so what we have is integral from pi over 6 to pi over 4, x times secant squared x dx. This is going to be u times v. Well, u is equal to x. V is equal to tan x. It's a definite integral, so let's put the limits. Pi over 6 to pi over 4 minus integral from pi over 6 to pi over 4. V times du, that's tan x. And du is just dx. Let's label these. So u is equal to x, that's u. 6 squared x dx, this is dv. And this is equal to u times v, that's u is x, and v is tan x. And minus integral v du, tan x is v, and du is going to be just dx. That's du. All right, so what we get is x tan x minus integral of tan x dx. Well, we can rewrite tan x as sin x over cos x. This will allow us to apply the substitution method to solve this integral. Sin x over cos x dx. And let's not forget the limits of integration. That's from pi over 6 to pi over 4, pi over 6 to pi over 4. All right, so we're going to apply substitution rule to this part to evaluate this integral. So we're going to let u be equal to cos x, because its derivative gives us the numerator. Du is equal to derivative of cos x is negative sin x. Let's divide both sides by negative 1, and we get minus du is equal to sin x dx. So let's label this part as, say, triple star. And what we get is integral sin x dx, that's minus du. Divide by cos x, that's u. The minus comes out, and we get minus log of u. And we get minus log of cos x. All right, let me put this in a box and label it as triple star so we know where everything goes. And now let's put it all together. And we're going to get integral from pi over 6 to pi over 4, x secant squared x dx. That's equal to x tan x plus log of cos x evaluated from pi over 6 to pi over 4. And look at the last page, you can see how the minuses will cancel out. If I was to write this here, we get x tan x minus minus plus log of cos x. That's like the full answer. And then we evaluate from pi over 6 to pi over 4. All right, before we can evaluate this integral, we need to have some special triangles. So let's go over those. So we have the 1, 1, root 2 triangle, 1, 1, root 2, and the angles are 45, pi over 4, pi over 4, 90 degrees, and 1, root 3, and 2, and the angle opposite 1 is going to be pi over 6, and the angle opposite root 3 is going to be pi over 3, 90 degrees. All right, so these are the special triangles. The 45, 45, 90 triangle and the 30, 60, 90 triangle. So let's substitute these in. Substituting the upper limit in, we get pi over 4, tangent of pi over 4, plus log of cos of pi over 4. Let me rewrite this on a lower line so everything is easier to see. So we get pi over 4, tangent of pi over 4, plus log of cos pi over 4. Now, substituting the lower limit in, we get pi over 6, tangent of pi over 6, plus log of cosine of pi over 6. All right, we know tangent of pi over 4, that's just opposite over adjacent, and looking at the first triangle, that's just going to be 1 over 1. So this part is going to be just 1. Cosine of pi over 4, that's adjacent over hypotenuse. From the first triangle again, we get 1 over root 2. So we get log of 1 over root 2. And tangent of pi over 6, that's going to be opposite over adjacent, that's going to be 1 over root 3. So this part is 1 over root 3. And cos of pi over 6, that's going to be adjacent over hypotenuse, that's going to be root 3 over 2. So the answer is going to be pi over 4 times 1, that's just pi over 4, plus log of absolute value, 1 over root 2, minus pi over 6 times 1 over root 3, plus log absolute value, root 3 over 2. Now, because these quantities, namely the 1 over root 2 and root 3 over 2 are positive quantities, we don't need the absolute values. So we can just rewrite this as pi over 4 plus, actually let me just make things easier and just change these to a bracket and log of 1 over root 2 and change this one here, that's going to be a log of root 3 over 2 because we don't need the absolute value. And we have a minus in here, pi over 4 plus log of 1 over root. And let's put the minus here, and that's the answer. That's the answer for the definite integral. All right, thanks.